The floor is yours.
Thank you for the chair for introducing me. First of all, I would like to appreciate organizers for organizing such a wonderful program. I feel grateful to share my findings here at the ICGS Bangalore under the program Quantum Trajectories. So this is a joint work with Professor Prabha Mandyam, Professor Nicholas Gerhard, and Professor Siddharth Domka. Vismay and Udit are my colleagues. Yesterday, this paper got appeared in the archive, and our group aims to develop faster and effective methods of noise characterization and mitigation techniques. So, so our noise characterization and mitigation techniques are as follows. So our method designed especially for to extract noise spectrum associated to the dephasing relaxation noise. We don't care about the T1 because because the noise spectroscopy for T1 is not important, because the way we correct the T1 can be by improved qubit fabrication or via qubit error correction. So the architecture of the transmon were already been discussed in this program by Professor David DeVinzo and Benjamin Howard, and the error correction for the T1 is already been discussed by Professor Prabha Mandyam, Devjyoti Biswas, and Saurabh Gupta. So our focus for this method is to basically estimate and mitigate this dephasing noise. So the key element of our method consists of a neural network where this coherence curve acts as an input to a neural network, and it gives noise spectrum as an output. And from this analytical expression, we can check the performance of our network, that how well the prediction has been done. So over here, the noise spectrum describes those noise sources which have stationary and Gaussian noise sources. And once we know the knowledge of noise spectrum, we can optimize the DD pulse, which have been used to probe the T2 decay curves. So here's the flowchart of the program, the method. So the purple indicated by the previous method, again, Professor Siddharth Domkar was the part of the method. So where the method starts from by generating training data to train a neural network to learn this equation, this integral equation. Then using this trained network, we do the predictions. So once the neural network is trained, then we do the experimental acquisition, and from the experimental data, we can predict what are my experimental noise spectrum, and since the process follows. So during our optimization of DD pulse, we can also have a quick check whether we have got a right right noise spectrum or not. Once we are okay with the check, then we can do our rapid time dependent noise spectroscopy. So here the prediction by the neural network is almost instantaneous. So this gives us the quasi static profile of our noise. So this is the outline of my talk. So first I will give some preliminaries and motivation behind the work. Then I'll discuss the results, the performance of our neural network on test data and on the IBM hardware. Then at the end I'll show you the time dependent noise spectroscopy that we have got. And if I have a time, I will also touch on the outlook. So first of all, the decoherence, the loss of coherence is due to the unwanted interaction with the environment. And this whole part has been already been discussed by Professor Nina Meany. So this noise process can be mathematically described by CPTP map. But here, there are two noise channels which are very important in the context of superconducting qubits. First is amplitude damping channel, which has these two corresponding noise operator, cross operator. And the second important is phase damping channel. If we consider an arbitrary state in a standard basis, then we can see the effect of these two quantum channels on the qubit turns out to be this density matrix, where we can see this density matrix element picks up a decay factor, and we can correspondingly see the contributions of both channels in the density matrix, where we can see the diagonal term picks up the noise due to the T1 process, and off diagonal decays because of the both quantum channels. So we'll come back to this matrix element, because there are some additional noise sources such as colored noises, for example, lower number of F type of noise, noise due to the local two-level fluctuators, which will modify this green particular part of the density matrix. And we'll consider some general form. So here are the table of some common stochastic noise sources in our transmon architecture. which we can find from this paper. It's a beautiful review paper. I would highly encourage. And we can see the list of the dominant noise sources and their corresponding noise spectrum. So this is some kind of an educated guess which we can use in training of our neural network. Okay, and we can see the corresponding coupling with it has with the qubit axis. So this is a geometrical picture of to understand how the decoherence happens. So first block sphere is just a representation of qubit state. Second block sphere represents energy relaxation whenever we have noise sources which get couples to the transverse axis, which give rise to this excitation and de-excitation. But because of the temperature which we work on, which is 10 millikelvin or 20, so the rate of excitation is 1000 times smaller compared to the rate of relaxation. So this gives overall amplitude damping channel. And the third block sphere represents the pure dephasing. Whenever we have noise sources couples to the diagonal axis, it gives rise to dephasing. And the combined effect can be seen as a transverse relaxation. But since we have a presence of this charge and flux noises, which results to this 1 over f type of noise, which is singular, very close to frequency equal to 0. Thus, we cannot. So this block Redfield description of decoherence doesn't hold longer. Now we have this density matrix of qubit in the subjected to 1 over f type of noise, and we can see this dephasing term has got a different functional form. Here is a more general functional form where we have non-exponential decay functions, and it has a relation with the noise spectrum as shown here with this integral equation. If you see this integral equation very carefully, solving for this noise spectrum is not easy from the coherence curve, but the inverse problem of getting a C of t from S of omega seems easy. So this motivates us to employ this neural network method to act as a functional approximator to estimate S of omega from the experimental C of t. This is the coherence curve of the qubit. So now I'll talk about how we generate training data. So first of all, I showed you the table in which we saw the various forms of the noise spectrum. So we take this as an educated guess and we construct a noise model. Over here we have considered white noise, 1 over of type of very simple model, and we also did some smoothing at the cutoffs. We also did consider 2 cutoffs here. Then in this equation we feed this noise model, and we have considered CPMG 32 filter function, and we put that into the integral equation and we get the coherence curve. So that's how we artificially generate the coherence and C of t pairs. We also do add some Gaussian noise, some random Gaussian noise to simulate experimental data. And to constrain our training data to get higher prediction accuracy, we fit these coherence curves to these test exponentials. And so these are the range of coherence in my training data. So this acts as a kind of a selection rule. When I choose a qubit from IBM, I would consider qubits of this particular range, for example 200 to 300 microseconds, and probably the p which is very close to 1. So the more the dephasing noise, the p value contribution would be more. So I'll go to the next. So this is the summary table of our constructed neural network. As we can see, it is an autoencoder type of a neural network, and this table describes the layers of my neural network, where we can see an alternate of convolutional max pooling, which basically kind of progressively extracts the features from my input layer. And then we have next alternating layers, which are the convolutional and the upsampling, which basically what it does, it restores basically, it restores the features. It restores the original dimensions of the input and also enhance the features. Then followed by the flattened and the dropout, and we have dense noise, dense layers. So in total, we have like these many parameters, a lot of parameters, and the input size is 150 and the output size is 501. Okay, so this is the summary table of our convolutional neural network. And now we'll see the performance on our test data. So here I've randomly chosen 5 input test data, and I asked the neural network what is my corresponding noise spectrum. So here the dashed lines represents my network prediction. Okay. Then once I have this prediction, I'll put back again into this integral equation to check how accurately I have estimated my noise spectrum. Here you can see the dashed line represents the curves that we have evaluated after the prediction. So here the solid lines are the test data and dashed lines are the predictions by the neural network. And we see that the prediction accuracy is centered around 3.8, uniformly distributed, and our training takes just 75 epochs. And the way we calculated this error is the mean absolute difference between the prediction and the test. So next we'll go to the experimental data acquisition. So what experiments we need to perform to extract a coherence curve, which can be act as an input to a neural network. So over here I have shown two simple experiments, that is T1 experiment and T2 Hahn eco experiment. But in our case, we have considered 32 pi pulses. Here I have just shown only one for the simplicity. So here you can see we do state preparation, then we wait before we do a readout. So the x-axis represents the delays and y-axis represents the population of Cat1. So these are the two simple experiments which we can measure out the various relaxation times or correspondingly decay curves. So now we'll check the network performance in our IBM qubits. So here's the data of T1 experiment, and this is the T2 experiment. Here I have considered 10 qubits. For each qubit, there is one decay curve. On purpose, I have shifted every curve by 0.1 for the clarity, so that we can compare the curves among them. So the thing is that we are interested only on the dephasing part, so we have to remove the T1 signal from the T2 signal, because T2 signal consists both dephasing as well as T1. So here is the post-processing of the experimental data. So the dot lines, so the dots represents the experimental data, and here we see the solid lines. These are my neural network predictions. And how do we get this neural network predictions? Since we have this dotted curves, we feed that to our neural network, which gives us the noise spectrum here. Then we again put back into this integral equation to get this solid lines. So I have picked one of the this one of the curves over here to see the prediction errors. So we can see the accuracy loss is within again 4%, and we can see it's like symmetric about 0. So which again shows that it's mostly limited to an experimental noise. Then once we know what are the once we know the underlying noise spectrum, then we can basically define an optimization problem. We can see from this integral equation, since we know what is this S of omega, we can optimize the parameters of f of omega t, which is a filter function, to basically minimize this whole integral, which defines this decoherence. So over here we have used SciPy optimizer using this SLSQP algorithm, and we have found the noticeable improvement in the optimization algorithm, just because the underlying noise spectrum is heavily white noise dominated, and we can see how the optimization is trying to reduce this original filter function got splits into two segments, and this higher harmonics tries to get overlap into this particular region. If you see very carefully, the experimental curves here is closely matches the prediction by the optimization algorithm. So this kind of a check authenticates that the predicted noise spectrum is very close to the actual noise spectrum. So this was the check, like are we getting similar coherent curve at least? Because if you see this, despite of implementing this arbitrary shape filter function, we still get coherence curves which are very close to each other. So this kind of an authenticates the that whatever we have, the noise spectrum we have predicted is indeed very close to accurate. In this experiment, we have implemented CPMG 8 because based on the cutoff value that what we see here, turns out that CPMG 8 gives us the maximal advantage. And so this is rapid noise spectroscopy results. So here we have, it's just last. So I'll just finish in a minute. Okay?
Sure.
So here we can see we have successfully recorded the variations in the T1, T2, T5 relaxation times and the corresponding noise spectrum. And we can see that the noise varies significantly and noise spectrum is white noise dominated. And the discontinuities that we see here shows that it is, I mean, I think it's a little wrong here. This X mark should be here. There is some formatting mistake here. Okay. So this jumps which you see here is because not they are entirely interdependent or they are not entirely time correlated. So this model effectively, this noise spectroscopy model effectively extracts something called as quasi-instantaneous noise profile. And I mean, I'll skip the outlook, but I'll just briefly highlight.
Finish.
Okay, so okay.
Take your time. Okay. It's the last talk. We are not in a rush.
Okay. So since the so our method is universal and it is hardware agnostic, we can again implement this whole protocol to the NV centers, and we have found much better results compared to the Transmon. And we hope that this study will help us, in examine and benchmarking other quantum systems. And this characterization can give us some insights to improve the engineering aspects, particularly dephasing the noise sources. And we can do the advancements in the filter function by we can improve the fidelity by advanced gates like drag pulses. In our case, we have used square shaped pulses, but we believe that maybe using these gates will get more better prediction accuracy. Then we can have more better filter function formalism. And using FPGA, we can have instantaneous error mitigation techniques we can potentially develop. And most importantly, the noise spectrum that we have generated is intricately linked with the error rates in the cross picture. So this can help us to do more better qubit environment simulation and can also help us in noise adapted QEC protocols. So we believe this trained model can help us to get time dependent QEC in the near future. So these are the members of our group: Professor Siddharth Dhumkar, Professor Nicholas, Professor Prabha, and these are to my colleagues. And thank you for your attention. Okay, I'll
questions.
Yeah.
Hi. Thanks for the talk. I would like to know how you calculate the error that you say is 4% from. I think you got the data
error?
from IBMQ, right?
This error, right?
Yeah.
So basically, we take absolute mean difference between this experimental and this predicted.
So, what do you mean by so you look at the coherence
Yeah.
from the experimental data.
Yeah.
And then plug in the. So how what's the predicted one came from?
The solid line which you see is the predicted one.
Yeah. How does it come from?
So the predicted one comes from, let's say you had this dotted curves, right? These are the experimental data.
Yeah.
We feed that to a neural network, and that gives me the noise spectrum. Then again, we put back into this integral equation. So that gives us the solid line.
And so you call that as an error.
Yeah, and we say that that's predicted by the neural network.
Okay, I see.
Because the neural network didn't know about this, right?
Sure. What do you think? Okay, one more question is like when you say that the noise of the IBMQ fluctuate over time, right?
Yeah.
Do you know what's like time scale and
so these time scales are in the we are talking about in microseconds, like 10 to 20 microseconds region.
You say 100?
Yeah, because I can give you a very quick calculation. So the evolution time that we have taken here is from 2 microseconds to 720 microseconds, and there are 150 data points, so we can divide and check.
Okay.
So that is the size of this one cell.
Okay. I'll talk later. Thank you.
So another quick question. So maybe I misunderstood, but all your results are based on the characterization of single qubit noise.
Yes,
Is
yes.
that right?
Yes.
So could you comment on how what are the prospects to scale up and to look for correlated noise among many qubits?
So we, in that particular case, we need better model. That's the only change here. We need to have more and more better noise model here.
Mm-hmm.
So here I have taken a very baby step of the noise model.
Okay. Thank you.
We have plans to improve this. And I was very lucky to get this prediction close enough. Maybe IBM truly had this functional form.
Thanks.
Thing is that this optimization that we have talked here should notably be considered, because IBM is T1 limited, but we have other systems like Rigetti and NV centers. They are not T1 limited, so we can see better improvement here.
More questions?
Yeah.
I have a quick one. You use this model for dephasing, which has noises at different frequencies. And as a result, it generates you dephasing that maybe not exponentially going, but in some of the curves, you had a flatter region at the beginning.
Oh, this, okay. So, right?
Can you go further?
I mean,
where you had multiple exponentials, you checked the fitting by neural network predictions.
Oh,
Here, if I look say at the top curve,
yeah,
it starts not as exponential on the left plot.
Okay.
On the left plot. Here it starts not as exponential, but slower.
Yeah, correct.
And then it becomes kind of exponential. Is it because your noise is frequency dependent, or is it for a different reason?
So in this case, we can see that's a stressed exponential. So in this case, it's like, so we can see the difference in the P. For example, here we have talked about, yeah. So difference comes in the power P.
Thanks. So my question is, should we expect something like this also for the relaxation channel?
Just a minute. So the problem with the relaxation channel, energy relaxation, they are irreversible and non-unitary. So we cannot apply some unitary operations to correct them or reverse them. But in the case of dephasing, they are like unitary reversible effects. So we can.
Nevertheless, I would imagine that coupling comes from relaxation comes from coupling to various quantum channels, which can quantum systems in the environment. They could have their own frequencies and therefore spoil this beautiful, simple Markovian picture of exponential decay. Or not spoil, maybe improve, make it less trivial to analyze. Should we expect something like this? What do the noise models
I have no
say?
answer currently, but I can understand. But yeah, I don't think so I can answer now.
All right. Thanks. Any other questions? In that case, let's thank the speaker.